Erdogan over there.
Okay, hi there. Hi.
Hello, everyone. If you are ready, we can start. Dear guests, welcome to Online Design Talks organized by AKDO. Today we will host architect Amin Taha from Work and Amin Taha Architects Office from London, and architect Gökhan Karakuş from E-Media Design with their speeches titled of Contemporary Architecture and Structural Stone. Please keep your cameras and microphones off during the event. If you have any questions, please write down to the chat box on the right-hand side. Your questions will be asked towards the end of the event. Now I leave the floor for Erdoğan Akbulut, then event will be started. Have a nice session, everyone.
Thank you.
Good afternoon, everybody. Welcome on board. Thanks for joining us, Amin, and thanks for your efforts, Gökhan, also. Since this pandemic issue, we have been organizing these webinars, and not only in Turkey, but we extended this to international platform. So once again, thank you, Amin, that you accepted our invitation and joined. I know you like stone, and we are one of the largest stone manufacturers out of Turkey, and we are not limited to only conventional methods like the regular stone 2cm, 3cm. Despite of your reputation, we are also minimizing the thickness of the stone, where we are trying to make it widespread throughout more people who can afford all these stone jobs. So, but on the other hand, I would like to hear your opinions besides your structural stone works. If you also enlighten us about what you think about these thin stones, laminated items, whether you can use those things in your projects. So I would like to hear your opinions, and I leave the word to Gökhan, who is the moderator, who is a well-known name in Turkey and also international platforms. So thanks for your contribution, Gökhan, as well. Now,
thank you.
Please.
I want to thank Erdoğan Akbulut, who is a friend and a work colleague for now almost 12 years in the stone sector. I blame him somewhat for bringing me into stone, because he brought me into stone 12 years ago, and I have not been able to get out of stonework. So this is, it's both very interesting, but it's stone is a very heavy material. It requires a lot of thinking around it. So I think you can devote one lifetime just to working on stone. So within all the works of stone and stone architecture that I've been involved with, editing magazines, curating exhibitions, one thing that's always occupied me has been structural stone, using stone as a structural, expressive part of architecture, which was actually the way architecture was built for thousands of years. If you take into account the stone monoliths of the Bronze Age in Turkey, we have a lot of them, and in Northern Europe, Stonehenge and similar monolithic structures exist. So, but in the modern period, obviously things changed, and stone became a cladding material. And the stone sector globally operates today to organize stone in architecture and construction as cladding. So just over the last 10, 15 years, it's been interesting to me to see a number of architectural practices slowly moving over to structural stone for different purposes and effects. And one of them is, one of the leading figures in this of late, over the last 5, 6 years, has been Amin Taha, and he's with us today. And it's very exciting. I mean, I've seen Amin just in passing in Venice once, but I'm following his work and the work of his colleagues, like that he's been working in structural stone, including this recent exhibition at the Building Center done with Webb Yates and the Stone Masonry Company. So let me just do a quick intro to Amin Taha. Amin Taha has an interesting background. He was actually born in Berlin before German unification in East Germany. So he grew up in a kind of Eastern Bloc world, which one day I'd like to talk to him about. He then immigrated to the UK in the late 90s with his family in late 1979. He was educated in architecture in Scotland at the University of Edinburgh, which is kind of interesting pedigree there, I think. Scotland and its architectural traditions are a bit different. And he worked with a number of very, very good firms and practices, architects, Chris Wilkinson, which today is now Wilkinson Iyer, Zaha Hadid, which is now Zaha Hadid Architects. He moved to create his own practice in 2003, Amin Taha Architects in London. And then most recently in 2014, he has created another practice, more of a collaborative practice, Group Work Plus Amin Taha. And he joins us from his office in London at 15 Clerkenwell Close, which is a building he designed and constructed. And for me, as I said, Amin Taha's work represents a kind of very interesting but small group of architects working with this medium of stone. So Amin Taha is going to give us a little bit of a lecture or talk on his work and some of his work in contemporary architecture, structural stone architecture, and some of the work that he's exhibiting at the Building Center in London, which the exhibition has just reopened, right? I mean,
correct. Yeah.
Okay. So
Amin Taha. Yeah. Hello. Thank you for joining us. Thank you for that, Gökhan. I'll share the, if I can work out the technology, I'll share our presentation and go from there. Okay. There we go. Okay, so this is our practice, group work. And I'll explain how we came onto structural stone. We began with a project at Caroline Place, which is a house in central London, adjacent to Hyde Park. And it's a house that's built after the war. So you can see there in that aerial, there's parts of that area that were bombed during the war. And this is a replacement house that had lots of modifications to it. Is that sound? Is that me?
Hold on.
I think you. Well, let's carry on and see whether that sound goes off. But it seems to be clear now. So it's a house really that's mostly about internal modification. Lots of cabinetry and some stonework. So the stonework really started as a reintroduction of some of the fine stone that was found in that house, namely travertine. What we could do with that. So as you can see here, it's partly internal, partly external paving and floor finish, and then bringing that sort of the variety of finish internal. Creating a staircase out of that, a new staircase that would rise up through this the new basement and new roof extension, and working with both stonemason and engineer, who reintroduced the idea of these reciprocal part cantilevered, part reciprocal staircases. So essentially, it's a medieval staircase technology that modern engineers and architects had lost, but was reintroduced more recently, specifically by Price and Miser in the late 80s. So most of the house is a reintroduction of cabinetry. Some of this is by the same masons, as it were. So they're obviously skilled. Some of you will know. A lot of the stonemasons are skilled in cabinetry or timber work as well as stone, because often the formwork for that stone would have to be done in timber. Typical sort of interior finishes. And there's our staircase. Now, the key thing here is that the staircase, apart from using some of that medieval technology, what we quickly realized as masons is that these staircases tend to have about 40% wastage. So what we worked out with that mason was to take a block and cut the underside, or split the block at a curve. So not a straight line, but a double curve. And that would then unfold that block and allow you to get 2 treads instead of 1 out of the same block, and therefore save the material. looking at how we split that block, we realized, well, why not retain the finish of that? Given that we're thematically coming out of the basement, the subterranean area, and working our way up and refining the underside as we go all the way up the building, why don't we just leave that rough quarry, crude stonemason's finish as the finish to emphasize that theme, as it were? It's a view looking down. That's the new subterranean basement area of the house. And they're showing you how we split those blocks and how they might fit together in the yard before they were assembled on site. And here's our stonemason assembling that from the basement upwards. One of the things we saw while we were in the mason's yard investigating how we might put this together is this very large limestone block. So it's a subdivision of the master block that's been done obviously with drill splitting. And looking into the stone staircase introduced us to something that most of us, we don't get educated in, which is stereotomy, which is effectively the pattern making of cutting stone and other materials, specifically here stone. And obviously how that was effectively the method for medieval stonemasons all the way to I guess the late 19th century, before concrete and steel became prevalent. This is an example of the staircase in Graz, a sort of double interlocking spiral, helical stair. But what we found fascinating was there's obviously, I don't know, some of you might know Abel, a 17th century French engineer. That top right-hand image is a drawing of his, where he's suggesting that if you can't span a space in a single piece of stone, you could cut out smaller pieces and make them reciprocally, in other words, rest on one another and span in a flat arch. I mean, an example of that is directly below, where it's not interlocking in that grid manner, but it's still interlocking to effectively give you a flat stone soffit that then takes the loading down in those sort of scalloped arches. And I guess some other examples there, earlier ones of quinches and other forms of geometry that then take that load down. This is all very fascinating to us. We weren't sure how relevant it could be. It's very easy to obviously introduce that into what can I say, high-end luxury dwellings. Is it applicable anywhere else is the question. Naturally, in the introduction, we were talking about how stone tends to be used today, which is this method, effectively stone cladding. So you can see there in the drawing on the right-hand side, your superstructure might be concrete, it might be steel framed. You would then clamp into that. You'd have to clamp through insulation, vapor barriers, waterproofing, and all the rest of it, until you get to then a set of rails onto which the stone is fixed, and the stone itself would be somehow bonded to another set of rails or other system. Quite a lot of energy, if you like, effort and cost in doing that. And that's all we know of stone today, and that's a tradition that's evolved really for the last 100 years, since the late 19th century, effectively with the states putting up steel frames very quickly and then being able to clad those steel frames instead of waiting for bricklayers and stonemasons to come up against the frames with self-loading facades, self-supporting facades, actually cladding onto those and hanging any facade system off that. So this is the result really from that system over the last 100 years. For us, the question then of whether you can build in stone as superstructure and economically compared to, say, the luxury of that staircase, investigating it for a well-off client, as it were, arrived with Clerkenwell Close. Now, Clerkenwell Close sits outside what was the old medieval city of London, on a site which was a Norman nunnery. So there was nothing on the site until the Norman invasion, and the Normans built this Augustinian nunnery. And they introduced the idea of using stone, cut stone, limestone, that's fresh out the quarry, so relatively soft to carve, and interlocking the stones. So after 6 months, a year, they calcify and become incredibly strong, compared to, say, rubble wall construction, so rubble walled fortifications. Now, obviously, once they gain power and stability in any area, that same method, technology is used for other buildings of status, specifically here religious ones. So Clerkenwell, the nunnery stayed there for 500 years until Henry VIII, and from left coming down, top left, is Henry VIII's man, the Duke of Norfolk, who was sent to take on, get rid of the nuns essentially, and take the abbey himself. Now, from then onwards, effectively, this whole area changed. Year by year, the medieval abbey vanished and was replaced by a palace for Oliver Cromwell, who's next on the left. Eventually, Victorian period, Oliver Cromwell's house was vanished. The whole street, whole areas again changed with mass housing during Victorian expansion of London. And there's William Morris, who then, this area had become well known for printing presses, and there's William Morris who purchases a building and turns it into what he calls the 20th century press. You can see directly below that, that's the building that's still on site today. It's now called the Karl Marx Library, because actually Karl Marx wrote for William Morris's 20th century press. And even Lenin used the press for his Russian language papers. And today, any Labour Party marches normally start on the 1st of May from that site. So it's an area that's, because it's been out the side of city walls, was slightly freer in terms of its laws for radicalism, printing presses, revolutionary ideas, if you like, all the way until after the war, when certain boroughs of London, including this one, lost about 50% of their population, and things became, if you like, a little bit more conservative in outlook. This is what was left before the Victorians demolished. This is Oliver Cromwell's house before it was demolished on the close, effectively our neighbour on the site. And then the typical buildings that were on the site, if they weren't the abbey proper. So if it wasn't the nuns' accommodation, but the servants to the nuns and the stables, it would have been this sort of structure, timber structure. And our initial designer response, as well as obviously taking on board various environmental criteria, all the other aspects that all of us typically as architects use, was to suggest to use an engineer's bit of software, which is a self-learning algorithm, to say, well, if we need glazing for office building or residential, typically those glazing units will come with some sort of aluminium or mild steel structure, substructure that's bonded, clipped, fixed, like a curtain wall, if not a curtain wall, to the floor slab, and then the superstructure behind that somewhere. It occurred to us, so supposing you take that typical unit system and say, strip it of all its metal, and you just have a double glazed unit, and you take that metal as if you've melted it down, and you give it to the algorithm and say, we have this unit system of glazing that we're looking at, and we want to reapply that metal, part of it, if not less, as superstructure. And the algorithm effectively gave us a grid of metal that we put a fireproofing on, and then a hot bronze applied finish as a self-weathering system. And the algorithm effectively gave us a grid with some diagonals, because the load path on the building had to stop it twisting. And then generated what you can see if you look carefully, some areas that require less metal and some areas that require more. So quite an interesting modulation. And in some respects, alluding to the idea of those medieval timber structures. This is very, very popular with our planning case officer. Unfortunately, there was a new conservation officer who'd arrived, and he didn't understand the idea at all, or the illusion. And he read the conservation area guidelines. Every borough has them in London, which any new buildings in conservation areas should be made of the predominant material in the area. Now, he hadn't actually been to the area and understood it was mostly brick, and even then, mostly 1960s, the 70s and 80s brick. But he had seen a picture of the church, and the church is limestone. So he said, I'd like it in limestone, please. And we don't have any prejudices against the materials. And I thought, well, let's investigate that. So we looked at, talked to our masons who we'd done the staircase with and said, look, we're looking at the idea of making a building in load-bearing stone. We don't want to do a superstructure that's concrete or steel and then clad it, because it seems like a lot of effort, a lot of cost to us. There must be a more cost-effective way of building in load-bearing stone. There aren't many examples in England at all. There's the parliamentary offices opposite the Houses of Parliament by Hopkins, which notoriously, because it's mostly bronze really than stone, post-tension stone columns, and then the spandrel is all brass on bronze. And that's notoriously, the cost of that notoriously, you could have replaced the entire elevation of that building with 5 top range BMWs next to one another, and it still would have been cheaper. So notoriously, quantity surveyors will always use that as an example to demonstrate that stone is not cost effective. Talking to our French stonemason, they reminded us, or rather educated most of us, that in France it was called austerity construction. After the war, it was actually cheaper to build in stone than it was in steel or concrete. So we went to visit a couple of quarries after our engineer gave us some ideas of sizes of stones that might be required. And once we together calculated the volume of stone, we gave that to the stonemasons, and they said, look, we can supply and install the stone for this much money. That, as it turned out, was about 25% of the cost of building a steel frame or a concrete frame and then cladding it. Now, you have to remember, cladding it as an engaged facade means insulating and waterproofing it, fireproofing it, and all the rest of it. So the stone itself is superstructure, but effectively does all that at the same time. And that's sometimes difficult for quantity surveyors to understand, because they still look at it as if it's only the frame itself. Surely after that, cladding still has to be applied. And it takes some time to be able to run through the entire cost plan of a quantity surveyor and demonstrate that the cost of the stone, or the stone itself, is superstructure plus cladding and the waterproofing, weatherproofing, etc., insulation, all the rest of it, because that's what it's doing. It's performing all those functions. So our part of the reason it's inexpensive, especially today, is because if you look carefully at the cutting method, it doesn't take a great deal of labor anymore to cut the stone, extract it from a quarry. But what we discovered while we were there is ultimately there were 3 types of finishes that come out the quarry, and even today they're reducing. From the right-hand side to the left, that's the saw cutting that extracts the master block. The middle one is the sedimentary layer split, so it's the horizontal sedimentary layer just split open. You can do that one with a bit of pressure, and then the one on the far left is the drilling. So 3 types of finishes that come out the quarry, and occasionally you'll find fossils, ammonite shells, etc., and a quartz pocket every now and then too. The next step was to then bring those stones together and say, how are we going to hold up the slab? So we tested this in the yard with a metal boss that's just grouted. So gravity essentially sits on top of the metal boss, and then the metal boss is connected back to the floor slab. So our test said it was all going to work out fine. So on we went. And that's under construction. Floor slabs cast in, all on temporary props. And if you look carefully, you can see those black squares on the edge of the slab. That's the metal bosses, the receivers for the metal bosses cast into place, ready to receive the columns and beams. So our floor plan, ground floor plan, you can see there the perimeter of the exoskeleton. And of course, the advantage of an exoskeleton is that there are no internal columns. So the exoskeleton spans from edge by about 8-9 meters to the central core that stops the building twisting. And then the sort of final elevation in the 3 types of finish: saw cut, sedimentary, split, and drilled split. Here's your construction detail, for those of you interested in the technicality of it. On the right-hand side, the beam has a pocket cut into it to receive the metal boss. It's all grouted into place, and then that is fixed to another plate, which is then bolted into the floor slab. The thermal isolation is provided by a 40 mil nylon bar, and that's it really. It's reasonably straightforward. The reason for making an exoskeleton is principally because it makes the junctions of all window areas quite easy. In other words, you've got a curtain wall that runs down the entire facade and deals with weathering, i.e. rainfall and the rest of it. You don't have to be precise about every window frame. You don't have to do any more work to your stone either. This is it in its context, and part of the reason it got slightly had some controversy from a particular councillor who sits on the planning committee who hadn't seen it because it was done under the delegated powers of the planners, was that as a councillor on a planning committee, he's not particularly expert, but looking at this conservation area, at first glance, if you don't look too carefully, it looks like an ancient area, doesn't it? Well, every building you're looking at is from the 90s. They're all post-war, effectively. So they range from 60s, 70s, and 80s, and then a long break until our building there in stone. And all of them are concrete steel frame with half a brick of cladding suspended from each floor plate. And if you like, with some sort of attempt to look like they're Georgian or Victorian. That's it again from the bottom of the close, looking upwards and a bit more in detail. You can see that the detached area with the timber vent panels behind, and then in context of the church beyond. And some ground level details that remind us of what used to be on the site in terms of the medieval abbey. And some other details that allude to the connection of the abbey, even to, because there's a new church called St. James, to its connection to Santiago de Compostela in Spain. And the interior, that results from having a column-free space. And the use of stone then in other parts. And that structure effectively allows quite a deep roof area that has this what's called a blue and green intensive roof on it. So after that building, we were asked by Camden's planning department to help a developer on a site in a similar vein, as it were. So we actually doubled the height of the building there. Now, the key issue about doubling the height of building, especially in the UK, is that you then cross a threshold for fire. So limestone, it will survive a fire if you make the columns and beams big enough. And what we did was send limestone as well as basalt and other stones to the British Research Establishment for fire testing. If you bear with me, we'll just close the door on some work that's going on upstairs. Thanks. And what we found at the British Research Establishment was that we tested not just the types of stone, we actually tested their position. So if you engage a stone column and beam with the elevation, what that means is that part of the internal elevation is insulated effectively, because you're bringing your insulation internally, you're then lining it, whether it's plasterboard or something else. And in that condition, what's happening in the event of a fire is one side of the column and beam is actually protected from the fire, while the other three sides, external ones, if the fire is then penetrating a window, are being heated up, and that creates differential expansion and is likely to crack the stone, stress it, and cut the, yeah, just ask him to stop. Thanks. And with that differential expansion, it means you either have to, or you either can't use the stone, or you have to increase the mass of it, and therefore the cost of it. And therefore, we found basalt and an external skeleton is ideal for then meeting that fire criteria, structural and fire criteria. Now, what we also discovered was Clerkenwell, we'd actually began with a concrete floor slab and core for stability, but then had the limestone as exoskeleton. While Clerkenwell was being built, we actually finished about 3 buildings in cross-laminated timber. And of course, we were banging our heads against the wall, realizing, well, why on earth hadn't we made Clerkenwell's floor slabs and timber? So the idea with Finchley and all future projects, if we're not going to use stone throughout, is to potentially use CLT, cross-laminated timber, for its floor plates and potentially the core as well. And you'll see from the research project later on, I'll illustrate later on, the advantages of doing that. That's a render. This project's actually on site now and at ground level. So this is a research project. We weren't particularly ambitious with its height. So you can see at the bottom of the page, the tower, the green roof on it, that's ground plus 30 stories. We weren't ambitious because we'd only managed to demonstrate ground plus 10. So with the same engineers, stonemasons, environmental engineers, and cost consultants, we effectively proved that you could build. It's not meant to be anything extraordinarily special. It's deliberately prosaic in its form and rendering to demonstrate that you could substitute any office building, standard office building around the world, steel or concrete frame, with stone. And the purpose of that wasn't just to demonstrate you could, but actually, is it cheaper? Is it environmentally better? There it's its height. If you look at that top left-hand side, that's the plan, very simple, core in the center. We actually worked with people at Canary Wharf to get a brief for its ideal dimensions, floor dimensions, floor areas per floor for letting purposes. And that gave us the overall dimensions of the building. And then obviously they suggested also that maybe 30 stories is ideal for them as a sort of peripheral development from the core of Canary Wharf. In plan, those lines are actually pre-stressed stone slabs. Now, the answers we got from our sustainability engineers are what you can see there. On the far left-hand side, scenario 1 is everything in stone: floor slabs, core, exoskeleton, roof, etc. And then you bring your glazing in and fit out within that. And what you can see, obviously, compared to scenario 3 and 4, which is steel and concrete frame, in terms of carbon footprint, embodied carbon, there's obviously a significant advantage. Scenario 2 is the option where you have a stone exoskeleton, which is obviously a structure, but is useful for fire purposes, especially in this country, possibly under the same criteria in other parts of the world. But the internal floor plates are actually timber CLT. You can see there, at that point, it becomes carbon negative. Carbon negative to the extent that it's it completely swallows up scenario 4, which is the entire, a building entirely as a concrete frame. In terms of costs, then, under those scenarios, you can see there the stone alone is about the same as a steel frame structure, which then has to be clad. It's cheaper than if it was a concrete frame and has to be clad. But stone and a timber floor plate and core is cheaper still. So the purpose of this exercise was to demonstrate to large-scale developers, offices and residential, that building in structural stone is cheaper and obviously far more sustainable. If you're combining stone and timber, then it's carbon negative to the extent that it would actually be better to go around demolishing city centers made up of these buildings, steel and concrete buildings, rebuild in stone and timber, and you'd still come out carbon negative. Excuse me. Okay, now, with the exhibition, we were asked to invite some architects, other architects, practitioners. And well, some of you already might know Giles Paradin. He's based in the south of France. He's actually based in Lyon. A lot of his work is in the south of France. He's already building, has been all his life, building in load-bearing stone. You can see these low-level, low-rise structures all in large blocks. He tends to build in very large blocks because he thinks that this is the most cost-effective way of extracting the stone, transporting it, and getting it built fairly quickly. So for him, these blocks tend to be about 1 meter, 1.2 meters long, and sometimes 800 by 800. And in certain parts of France, on the Mediterranean coast, he makes these solid walls, i.e. there's no cavity, no insulation, because for him, for this part of the world, he doesn't need it. He doesn't need the thermal isolation, as it were. And what we also discovered from him was that he's already working on a tower in load-bearing stone in Switzerland. So that's on the right-hand side. You can see there stone piers, and on the right-hand side of the bottom, the keystones in stone too, as it were, the transoms. Now, I mentioned earlier that in France it was called austerity construction after the war. And Perrodin, Charles Perrodin, who you just saw on the previous slides, is a tradition actually that carries on from Poulon. So Poulon, after the war, took on the challenge of reconstruction, starting off in Marseille and challenging the burghers of Marseille with the idea that he could build faster and cheaper in stone than people were proposing in steel and concrete. Now, the thing is, after the war, in Europe especially, steel and concrete is obviously emblematic of the modern era. We're leaving 2 world wars behind us, the traditions of the past, and we're now moving forward with the new era, the modern age, and steel and concrete is going to be our signature, if you like, in doing that, politically, as well as obviously for the profession. Poulon had worked for Auguste Perret, as had Corbusier. So while Corbusier is building the Unité in Marseille, Poulon is building on the harbour side and in town. And you know, obviously, especially at that time with in-situ concrete, Corb was building probably 5, sometimes 10 times the cost of what Poulon was building in this load-bearing stone, lots of it low-rise. And in those sort of proportions. Now, you know, analysing those blocks of stone in those proportions, they look traditional, and that's partly because the size of stones you extract to be fairly economical, and the way you put them together in terms of lintels and keystones begins to dictate those sort of proportions, and we tend to look at them as traditional. That slide's really demonstrating the point where Perret, where top left, Louis Sullivan's innovation of steel frame and then bringing cladding up with it, terracotta tiles, cast iron tiles, etc. Auguste Perret, who then is an innovator in concrete, and for whom Poulon and Corb worked, and then obviously went in their separate directions. So what's the future hold? To the far left, that's that slide again of the French 16th century engineer, Abel, and his patents for reciprocal structures. In the middle is a firm called Anastas, who I think are Palestinian based in Lebanon and Paris, who've taken on that idea, the Abel idea, and created this flat arch of a reciprocal stone structure. This is another French stonemason. They're called Italia Romeo. They're actually based in Italy, in Trani, in Italy, who created another reciprocal structure. But in this case, they've taken a piece of software and taken it from a flat arch and turned it into a dome. You can see on the right-hand side there the identical form of those individual stones. And another Italian firm who are similarly using that sort of stereotomy, but using it with contemporary software and then robots to help cut out the stones. You could argue in a fairly efficient way, but obviously here there's a lot of holes in it. Coming back to your question earlier on thin layers of stone. Italia Romeo actually innovated this product, which together we've sort of called cross-laminated stone. And really what it is taking waste stone, the stuff that's left over from cutting, and packing it, bonding it in layers. And initially their idea was to use it just as a facade material, a thin facade that you could clip on. We talked to them and said, and they wanted to exhibit, I think this is how we met Gökhan, they wanted to exhibit this in Venice, and they gave us 4 weeks to come up with some ideas of how to demonstrate its capabilities. And we said, look, you're taking a waste stone, which is all in pieces, crumbled pieces, and then bonding it together. Really, you could, instead of laying it flat, you could lay it over any formwork of any shape you like. And if that formwork determines a structural ability, in this case of vault, why not do that and demonstrate it's not useful for cladding, but actually has its own structural ability. So this is a series of conical arches that demonstrated those abilities in Venice. I think that's it. That concludes the talk on stone, and I'll leave you to ask any questions.
Okay, so thank you. I mean, the trajectory there, I think, is from Abel to this is a very interesting trajectory. There's a lot of similarities over 600, 700 years, architects trying to figure out, piece together these geometries and the materiality into structure and architecture. My question to you is this effort at proving a certain sustainability, a certain economy from the stone. You mentioned earlier in terms of carbon footprint. In your example, you went from London to France. How much does this issue of the quarry versus the project, this distances and aspects factor into some of the cost analysis of stone? Because of the architects like Paradan that you mentioned, he uses for his work as somewhat close by. Can you speak a little bit about that, logistics, cost?
We initially went to a UK quarry, Portland, and most of London's built of Portland limestone, and asked them, can you supply this structural stone? And they said, look, we haven't extracted stone for that purpose for 100 years. We wouldn't know how to. We're not geared up to it, and we couldn't give you a certificate. You'd have to send the stone for testing. So our French stonemason said, look, we're only across the channel. Actually, Portland first said, if you just follow the stone seam, you know, people are obsessed with putting national flags in quarries. And they said, look, just remember this seam of bed of stone started off at 90 degrees and roughly at the equator several 100 million years ago. And depending on how deep you go down the quarry, it could be 600 million years or further up, 200 million years. And the further up you get more fossils, further down, fewer. Go across the channel and ask any quarry. They'll all have strength certificates because in France it's still used for structural purposes. So, and then reduce the quarries you're looking at to the strength you want, and then choose the stone according to fossils. At the end of the project, you know, we hadn't set out with the sustainability target in mind at all. It was a sort of side product, as it were, as we were developing the ideas. And our sustainability engineer one day said, you do realize you've saved 92% of your embodied carbon in the superstructure and cladding and all the rest of it that's associated with then finishing a building in stone. And we said, how on earth did we save 92%? That's incredible. He said, well, it would have been 95% had you brought the stone, had you got the stone from Portland quarry, from the UK. So he said, you've only added 3%, in the transportation from roughly the south of France to London. And we were scratching our heads still thinking, well, how on earth did we save that? And just think about it. And of course, eventually it dawns on us. There's inherently no embodied carbon in the stone at all. It's there, it's made for you. It's manufactured 250 million years ago. And really the only embodied carbon involved is extracting it from the quarry, i.e. the amount of effort you put into cutting it, putting it on the back of a lorry and then lifting it with a crane on site. So obviously, yes, it helps if you've got the quarry nearby, but in the bigger scheme of things, it's only 3% from the south of France to London. So I'm fairly relaxed about the transportation compared to obviously the alternatives of using steel or concrete.
Another issue that comes up with this process is the fact that you actually have to go into a quarry and start working with how the stone is cut and the different quarry cutting methods, which is not usually an arena that architects have any kind of leeway of any decision making, because it's based on the quarry and the stone producer's own business model and how much, what kind of infrastructure they have there. This methodology, though, and it's somewhat, I guess, is also echoed in masonry work since the Middle Ages, requires the architect and the designer to really jump into the quarry aspect of stone. And could you describe a little bit about how that feels as an architect to go into quarries, look at these stones, start figuring out how to cut them, change, move them, integrate them? Because it's not a standard architectural sort of process.
No, you're quite right. And similarly to the sustainability aspect, we didn't start off with the idea that we definitely need to go and visit the quarry and decide beforehand and dictate the finishes. Not at all. We were asked by Portland, look, go to France, check the stone color, if you like, and the texture of it. And that's all we were expecting. Pure, clean, saw-cut stone that's then had some finishing to it by a stonemason. Now, the stonemason typically will visit an architect's office with a whole range of finishes in small little tiles that he'll tell you range from riven, modern, parallel lines to part of that spectrum that's called natural. And natural, you'd imagine, is how it comes out the quarry. But you ask the question, of course, what they actually mean is they take a blowtorch and a chisel and they spall the top of the stone to make it look rough. And you get a variation of, plus or minus 5 mil or something. And that's what we were expecting. Just to visit the quarry, look at the color, maybe some fossils in there, and the rest of it would be done by the stonemason. So some of those blocks that you saw where we were in the mason's yard, where the horizontal and verticals would come together just to demonstrate how the metal boss would come in, that's what we were expecting before we went to visit the quarry itself. It's then when we visited the quarry and you see these master blocks, and the master blocks that come out are partly saw cut, partly drilled, and then these sedimentary layers. And the sedimentary layers have variations of plus or minus 200-300 mil on them. And you'll find fossils, ammonite shells, and all the rest of it. We were asking the stonemason, sorry, the quarry master, but this is fascinating. We're shown these tiles by the stonemasons, the finishes, if you like. We've shown natural, and we never, these ammonite shells are the size of your fist or bigger, the size of your hand or bigger. What happens to all these? Well, nobody comes to visit us. I mean, nobody comes. The stonemasons don't come. The architects don't come. Everybody wants clean blocks. The stonemason adds their value add in their finishes. So we just cut all the fossils off, crush them as aggregate for road fill, and supply clean blocks to everyone. And we say, well, does it cost extra to have these finishes? For you just to give us your quarry finishes? Of course not. Of course it wouldn't cost much. You'll probably be the first to use it like that. And to us, it answered a lot of questions because, one of the last design aspects is, well, how is that stone finished? Is it just saw cut with the final dressing, which hides the visible saw lines, i.e., looks very sober, what we expect of modern stone buildings, as it were. Or is it something else? Do we carve something else into it? And then, of course, the answer comes to you when this quarry master is giving you those three inevitable finishes: the sedimentary layer with all its fossils, saw cut, and hand drilling. And the next buildings we're looking at, we're going to quarries. And basalt obviously is not a sedimentary stone, so we'll not have fossils and all the rest of it in it. And some of the basalt quarries we went to are only, the lava spewed out maybe 10 years ago, and it's extracted in a very different way. So our tendency is towards not dictating, but actually asking the quarry, what is the easiest way that you extract the stone, and looking at that finish and saying, well, can we live with that? Can anybody else live with that? And more often than not, everybody can, because it is just the
why do you think they can? I mean, it's
well, not everybody can, obviously, because
there seems to be aesthetic there. I mean, want to push it into, it's not a style what you're doing. Obviously, it's working all these calculations and structural approach. So, but there is an aesthetic that is there.
Well, I mean,
I'm loath to kind of push it too much, but there is something there too.
No, there is, and you're quite right to put to identify it, because it's not unique to us. Obviously, it's culturally quite widespread. I mean, you go, the Japanese have formalized it into their culture, where effectively they're saying, look, every material has, whether it's artificial or even natural, has a spirit, and you should allow the inherent spirit, aesthetic qualities of those materials, the inherent ones, to speak for themselves, and whether it's stone or timber in this case. So I think everybody, we as people, builders, all of us appreciate that.
The haptic qualities, obviously, with stone, this is something that the stone sector globally always tries to emphasize, is the touch stone, and we know that the human body reacts differently to different stone surfaces, and the stone sector, and AKDO specifically, has worked a lot on figuring out how these different textures can be developed. So I think your work sort of fits in with that, and I think the architecture, we're living in a period of imagistic architecture, but architecture has always been very haptic, very physical. I mean, stone architecture has been very haptic, very physical. I think your architecture points to that in a meaningful way. And somebody that grew up in a lot of brutalist architecture in New York in the 1970s and 80s, Paul Rudolph, all these surfaces, and Khan, we got all this haptic quality. So to see it reemerge to a certain extent for me, I think a reemergence of the possibilities of architecture beyond iconography and icon and
exactly,
and other quality. And if anybody has a question, feel free to write into the chat. We have some people here online. Going to this last project, this is a thin stone. This is a thinner approach. And we know that the stone sector, Erdogan earlier was mentioning that from AKDO, that they're working on ways to decrease the weight of stone, because there's also different things you can do with stone, in these arches you see here. Can you speak a little bit about what you see as a potential of this aspect of stone architecture, that's lighter, more laminate, but on increasingly complex surfaces like the ones you developed here?
Yeah, so I mean, ultimately this is about making use of what's effectively a waste product. So normally this stuff would just lie in the quarry with people wondering what they're going to do with it, and it could be used as I said earlier, aggregate for all sorts of other solutions. So yes, it has a low carbon footprint. Yes, it's inexpensive, but as a consequence of the idea of bonding it, it means that it can be, these ideas of fibrous cement, for instance, being very thin and being molded into certain geometric forms that are effectively self-supporting. They're not new. So it's doing the same as those, except here it's a waste product, that's stone. Obviously, as you suggested, it has a different feel to it. You know, when you're not just looking at it, but when you touch it. Here, there's 3 layers to it, so it's 30 mil altogether, just to span. I think these are about 6 meters. Span 6 meters in 30 mil shells, as it were. Now, there's not. I mean, we had 4 weeks to turn this around. So it's not overly adventurous, but you can imagine if you take a 3-dimensional bit of formwork, you could make some quite dramatic structures out of that, out of very thin stone. The next stage we took this was to help them with some research, which was funded by the Italian government, to then effectively make this like a cassette form. So there'd be an inside face, an outside face, and internally it'd be insulated. And you could make then out of this waste product a series of walls and floors and roofs, just like the CLT. However, unlike the CLT, which is effectively internal superstructure because you have to weather the outside, insulate it and weather the outside to stop the timber being exposed to the weather, here you could leave it exposed to the weather.
I mean, is this 10 millimeter each layer? Because I see 3 layers are attached. So, but was it bent?
30 mil, yeah. So it starts off, because it's all crumbled pieces, small pieces of stone. You know, you just pick them up with your hand. You could drop them through your fingers.
So with epoxy.
Yeah. Well, what you actually do is you put it in a. I mean, I'm sure Italia Remy won't mind me telling you how it's done, because there's
some pressure involved, I would think.
They've got a patent on it,
yeah.
Copyright and all the rest of it. They put it in a bag,
yeah.
and drop the bag across the formwork, inject the bag, and then vacuum out the air, and
yes.
that gets the bonding agent into every single crack. So it looks like marble because it's made of small pieces of marble, but actually the marbling is the bonding agent. So you can curve it 3-dimensionally. You know, sorry, three directions of curves if you wanted to. You could do what you like, as well as flat. If you want.
We did an exhibition here with AKDO, who also knows this methodology, but theirs was a little bit different in that that we took an existing laminate surface, we put it into the bag. Also, I'm not going to get too much into details about it because it's also a process, but the pressure around the form.
Yeah, we made it thinner. It's like maybe 3 millimeters, so we can bend this on the sheet.
There's some issues there to give the surface. This points all these activities point to 2 particular areas, which is working from the quarry as a kind of research and development, and having the engineers and architects come into the quarry and figure out what they can do there. And on the flip side, going into the factory and working at a very detailed way. So the stone sector is, you know, these possibilities of fabrication, design, and architecture are slowly coming to the fore. And I think these are highly suggestive of different architectures, because these things are structural. They don't need to be treated. You know, it's stone, so you can throw them, you know, as an outdoor material. Obviously, there will be, if you use in the interiors, there are issues of sound and other issues that you have to deal with. But I think for a period in architecture where the hegemony of concrete and steel, and obviously there's some efforts in timber, but this approach seems to have validity when you're in a geography where there's a lot of stone.
Yeah. And I mean, you know, somebody asked us fairly early on when we were, I think, at the exhibition and research, but surely there's a limited supply of stone. And I had to point out that the Earth's crust is the supply. Once we run out the crust and hit magma, then we'll need to worry. Of course, the stone sits on land, which belongs to people and has a value. So at some point, when the market decides that stone is the answer, the land value increases, and before you know it, it'll balance out.
Okay. Does anybody have any other questions? If not, I'll just sort of ask my last question, which is a kind of more general question. Obviously, this whole last period of history with the virus and everything has created a different mindset.
Yeah.
I'd like for you to speak a little bit about, the way you're working, and it's not just stone, but you're known for detail work. You're heavily when you do work, you work very much into the details of how things are constructed and built. Do you see this kind of approach, whether it's in timber, stone, ceramics, working with very high qualified fabricators and craftsmen like the Stone Masonry Company or AKDO here, where they invest a lot of time? Do you see any transformation or any kind of difference now? Because what I see at a distance is that it seems like people are a little bit more concerned about the environment they're living in. And this might start to affect us as an architecture community.
Well, I mean, interestingly, it's a perennial question. It's not. I don't think it's new today. One of our other talks, we describe how during the mid-16th century, Giorgio Vasari wrote the book on history of the most excellent architects, painters and sculptors. And that's effectively the first history of art in Western Europe. And it lasted for about 200 years. And really what he's doing there, he's listing, in his opinion, he includes himself, the best architects and sculptors and so on. But the way he does that is describes their process, their method. And he explains how each one was apprenticed to a master mason or architect, etc., and how they developed the skill and understood the materials themselves, and how they might come together. They eventually innovated because they started as apprentices, and through those innovations became masters in their own right. Now, that lasted for about or a grand tour of Greece and Rome, projected his analysis of ancient architecture to Egypt and Mesopotamia, and effectively said, look, in my opinion, Greek architecture of these white fluted columns and white sculptures, art and architecture is the best. It's all white marble, and remember the Greeks were democratic and all the rest of it. Now that superseded Giorgio Vasari, and what effectively it did, and you have to remember this is the period of the Enlightenment. So Winkelmann is the first proto-archaeologist who's mapping archaeological finds, but he does admit in his book that these are my opinions. So yes, this is the archaeology. You can't argue with that. It's very empirically studied and mapped and projected as new buildings. But then the rest of it is his opinions. So these are projecting monarchies of the various countries they're living in, working in. The idea of the art is associated, the art and architecture is associated with democracy. And what quickly happens is that the architecture is adopted as a style. So Winkelmann is a historian. He's not an architect. He doesn't understand the process of making. So he doesn't understand anything about the tectonics of putting buildings together. All he's doing is redrawing them, making them emblematic of a particular political idea, and then disseminating that. And what effectively happens in Western European architecture is that from then onwards, from mid-1700s onwards, is that you have styles. So styles become emblematic of political ideas. And of course, inevitably, one generation will challenge their father's generation and so on and so on. So every generation decides that we need a new style because we're better than the previous generation. So everything is as a result about the image and nothing to do with how it's put together. But of course, every generation has asked those perennial questions. what, is it correct? Is it justified? Is it authentic that we are creating this architecture based on images? And so you have theoreticians, whether it's Ruskin or Gottfried Semper, always asking these questions. And the answer obviously is, if we had architects and sculptors like Giorgio Vasari suggested who understand the tectonics, then you will get an authentic architecture. Gottfried Semper, Otto Wagner were looking for that. They realized the Industrial Revolution is occurring, and surely there's going to be a new architecture that comes out of these new materials and the new ways of living. But they're right at the front end of it, and they don't know how it's going to happen. So inevitably, what they do is just reuse some of the old architectural languages, and then inevitably, a generation or so later, people working with those materials might begin to innovate. But within no time at all, those innovations become just images that are emblematic of a period, and therefore just again a style. So I think the key is to have that connection with the quarry, the stonemasons, the specialists, because they are informing you of the nature of all those materials, the properties, the structural properties, the visual properties, tactile, haptic properties. And that gives you a menu of materials to work with, and hopefully create something that's then, as you say, authentic.
Okay, that's for me, very inspiring kind of way to end this talk. We always like to put architecture in a longer continuum, and I'm happy and to hear these the larger scope in which to talk about architecture, because that's also sort of kind of missing a lot. So thank you very much, Amin Taha.
You're welcome.
15 Clerkenwell Close, his building in London that he designed and works in. This is a continuing series of talks on architecture and stone, sponsored by AKDO. I want to thank AKDO and the team at AKDO Ashken Çağatay, and also at Gezinti for the technical organization. So thank you, everybody. If you have any other questions that you want to direct about this talk, I think this will be put on YouTube at a certain point. You can always direct it to AKDO or me, and we'd be happy to talk about stone, because we like stone architecture. So thank you very much, everybody. And
I would like to thank
you,
both of you. I mean, I would love to invite you to our showroom in London next time when this pandemic issue is over.
Yeah, let me know and we'll catch up. Okay. Bye bye, everyone.
Thank you.
Okay, thank you. Thank you very much.
Bye.
Bye bye. Thank you. Good.